Welcome to The Explainer. Now, August 20th, it's arguably one of the absolute greatest dates in all of mathematical history. It's this incredibly unique day that quietly bridges completely different centuries, completely different countries, and a handful of brilliant minds who are either born or who died on this exact date. And honestly, here is the truly fascinating part. Those specific minds, they fundamentally changed the modern world we're living in right now. Let's meet them.
August 20th. You know, at first glance, it might look like just another ordinary square on a vintage wall calendar. Maybe you've got a birthday party to go to, or maybe it's just a regular Tuesday for you. But in the mathematical universe, this specific date is an absolute goldmine. It anchors the lives of some of humanity's greatest problem solvers. These are people who looked at the total mess of the universe and just decided, hey, we're going to find the hidden rules making this all work. So our journey today spans this fascinating, honestly kind of unbelievable timeline, connecting three distinct years, 1905, 1972, and 2014. We're talking about three entirely different eras of technology and human thought, but they're all anchored to one single date. One date, and so many hidden stories. Let's start at the very beginning of this timeline and look at a piece of everyday magic I bet you used just this morning. Let's kick things off with a wonder question we literally take for granted every single day. Why does your phone's GPS always find the fastest route, even through hundreds of complex winding roads? You just type in a destination, and boom, a perfect path appears. You miss your exit, we've all been there, right? And the system recalculates an entirely new route in a millisecond. How is that geometric wizardry actually possible? How does your tiny phone understand the physical world so perfectly? Well, the answer actually takes us all the way back to August 20th, 1905. That's the birthday of Anna Henriques. At a time when the field of mathematics was overwhelmingly, almost entirely male-dominated, she was a true pioneer. She broke some major barriers as one of the very first women to do research at the prestigious Institute for Advanced Study. And her specific, highly theoretical obsession completely changed how we understand physical space.
Her foundational focus was on topology and something called knotted varieties. Okay, in simple terms, topology is basically the mathematical rulebook of how spaces and points connect to each other, regardless of what their actual physical shape is. Think about a subway map. A subway map heavily distorts real-world distances, but it perfectly preserves the connections. It doesn't matter if the track bends or stretches. What really matters is that station A links to station B. Henriques studied the intense mathematics of how these connection rules behave in highly complex spaces. And because of her early work unraveling these mathematical knots, we can instantly map complex digital networks today. From the architecture of the entire internet to your daily commute, we rely completely on the logic of connections she helped pioneer.
Topology is the hidden framework of our connected world. This is our first big takeaway today. Without Henriques mapping the invisible rules of how points mathematically connect to each other, our modern GPS networks just wouldn't have a foundation to exist. We would literally be completely lost. Okay, so we're still on August 20th, but we are jumping 67 years forward to 1972. The world has drastically changed. We've gone from paper maps and early theories to the absolute dawn of the computing age. And with that massive technological leap, a completely different, much more daunting mathematical challenge pops up.
Now, here's our next question. How do we teach computers to process an infinite amount of information without entirely breaking down? Think about modern artificial intelligence or massive cloud servers holding endless streams of global data. A machine is ultimately a finite box with limits. So how does a physical machine make sense of the infinite?
That answer lies in the incredible legacy of Karp, a brilliant algebraic logician who passed away on this exact date, August 20th, 1972. While most computer engineers back then were simply trying to build bigger physical hardware, Karp took on a theoretical problem that standard mathematics literally could not process.
See, at the time, standard mathematical logic could only handle finite, limited steps. It's kind of like trying to count every star in the universe, but being forced by the rules of math to stop at 1 million. The system just crashes when the dataset gets too massive. But Karp achieves something totally unbelievable. She created a comprehensive language allowing logic to handle infinite possibilities. This system is known as Infinitary logic. Instead of breaking when a formula goes on forever, she built a mathematical syntax that actually incorporates infinity. By extending formulas to infinite lengths, she laid the exact theoretical bedrock that allows our modern AI to process seemingly boundless datasets today without short-circuiting. Her lasting legacy is just so poetic. She gave mathematics a language to speak with infinity. Before her, our digital logic had these rigid, unbreakable walls. Because of her work tied to this very date, our modern computing potential became completely boundless. All right, jump forward again. Decades later, the date remains exactly the same. We go from 1972 to August 20th, 2014. We're in a different country now, firmly in the era of smartphones and facing an even wilder natural challenge. Let's meet our final brilliant mind. But first, ask yourself this. How do those weather apps right in our pockets accurately predict the chaotic, constantly changing path of a massive hurricane? The real world isn't some neat, controlled equation. Fluids mix unpredictably, atmospheric pressures are constantly clashing, and storms shift wildly from hour to hour. Like, how on earth do we bottle that natural chaos up and put it onto a little digital screen? For that one, we're looking to August 20th, 2014, and the passing of Bryce McLeod. He was a revered master of something called applied analysis, working between Oxford and Pittsburgh. McLeod didn't just sit in a quiet room studying neat, perfect geometric shapes. Oh no, he waded right into the absolute messiest, most unpredictable problems nature had to offer. His specialty was the mathematics of modeling change. Specifically, he solved these highly complex, chaotic problems known as nonlinear differential equations. Okay, if a linear equation is straight and predictable, kind of like rolling a ball down a smooth ramp, a nonlinear equation is like throwing a ball down a rocky mountain right into a rushing river. The variables are constantly interacting with each other, basically multiplying the chaos. In simple terms, McLeod wrote the math that tames those unpredictable systems. Whether it's the chaotic swirl of fluid mechanics in the ocean or super complex biological reactions, nature is incredibly messy. But thanks to his brilliant proofs, we can mathematically model and predict that natural chaos, sending life-saving weather alerts right to our phones. He found the perfect mathematical order hiding inside nature's chaos. He basically proved that even the wildest, most unpredictable storm out there still ultimately follows a mathematical rule. So when we zoom out and look across our timeline, the connective tissue of this single date is just astounding. August 20th gives us Henriques mapping our physical connections. It gives us Karp speaking directly to infinity. And it marks the legacy of Bryce McLeod, who tamed natural chaos. 3 entirely different centuries bound together by one golden thread. Every single pioneer we met today looked at an impossibly complex world and asked the exact same fundamental question. What is the pattern hiding inside the chaos? Because they dared to ask that, you hold GPS, infinite computing, and weather prediction right in the palm of your hand. So I'll leave you with this. The next time you look at a totally chaotic problem in your own life,